yes, I told you that too much of the fluid flow, too much of the flow rate will cause the turbulence, and it will also result in the entrapment of the gases inside the molten metal. And there is another very important problem which is observed in the casting process, and this problem is called the aspiration effect. And due to this effect, the air and gases are tapped inside the molten metal during its flow inside the sprue. So from this diagram you can observe that this is your pouring cup, and then the liquid is poured inside the pouring cup, and from there it flows into this down sprue, and then after that there is a runner, and then there is a riser, and after that there is a mold cavity. So fluid, the molten metal which you have poured here, it will reaches into the mold cavity. And you all know that this is a fluid flow. So in fluid flow, for any fluid flow, there is a very important, can say, the law which is given by the Bernoulli. So this is the Bernoulli theorem, which states that the sum of the energies such as the head, pressure, kinetic, and friction at any 2 points in the flowing fluid are equal. So within this flow from here to here, you can calculate the sum of the energy, and between any 2 points, the sum of the energies will be equal. So suppose you consider a point here, which is point 1, just at the surface of this sprue or your pouring cup, and if you consider a second point at the end of this sprue channel, so by the Bernoulli theorem, you can calculate this particular sum of the energy, which is H1 plus P1 by rho and V1 square by 2G plus F1, which will be equal to, again will be equal to the sum of the energies at this point 2, which is your H2 plus P2 rho plus V2 square by 2G plus F2. And here H is what is H? H is the height or the head, P is the pressure on the liquid, D is the density of the material, V is the flow velocity, and G is the acceleration constant, and F is the frictional head loss due to friction. And so if you ignore the frictional head losses, if you ignore the frictional head losses, it is assumed to remain, and the system is assumed to remain at the atmospheric pressure. So the pressure component can be neglected, and also F1 F2 will also be get cancelled, and finally the equation will be transformed into H1 plus V1 square by 2G equals to H1 plus V2 square by 2G. So this particular equation can be used to determine the velocity of the molten metal at the base of the sprue. So initially you can consider that the fluid velocity at the just at the surface of the this pouring cup, velocity of the molten metal is, you can consider to be 0. And at the so now you are interested in determining the velocity of the molten metal at the base of the sprue, which is the point 2. So let P1 be defined at the top of the sprue and point 2 is at the base. So if you consider this point 2, suppose this is point 1 and this is point 2. So if you consider this point 2 as the reference point, then the head at this point is 0. So here the H2, this H2 will become 0 at point 2, and H1 is the height, or it is the total length of the sprue. So when the metal is poured into the pouring cup and then it flows down to the sprue, its initial velocity at the top is 0. Consider that velocity to be 0 because comparatively it will be of very low speed. So finally this H1 can be equals to V2 square by 2G, and if you solve this correlation, you will have the velocity of flow at the bottom or at the end of the sprue, which comes out to be V equals to under root 2GH. So here the velocity component is dependent upon the this particular acceleration due to gravity and the height of the sprue. So at the base of the sprue, the velocity comes out to be under root 2gh. And now this equation under root 2gh, this equation tells us that the velocity of the flow increases as the fluid moves from opening to the end of the sprue, and particularly if the sprue is straight. So the sprue is straight. If the sprue is of straight channel, so it will result in the sudden pressure drop in the fluid flow. So if with increasing velocity and sudden pressure drop, it draws out the atmospheric air and gases evolving from the baking of organic binder. So this organic binder is present in the sand, prepared sand of the mold cavity. So you know that when it comes in contact with the molten or the heated metal, so the baking of organic material, organic binder takes place, and it results in the evolution of gases. And these gases and the air gets easily dissolved in the molten metal to cause the porosity and other defects in the casting. So aspiration effect is what is basically the generation of the gases, and then entrapment of these gases along with the air inside the molten metal, which will eventually will cause the porosity and other defects in the casting. So in order to reduce this problem, the cross section of the sprue column must be reduced as the fluid velocity increases. So in this diagram, you can easily observe that what is the shape of this down sprue. It is not straight, it is somewhat tapered. So why we are making the tapered shape sprue? This is the logical reasoning that with increasing velocity, there is a sudden pressure drop will takes place in the fluid flow, which results in the entrapment of the gases and air into the molten metal. And basically to prevent this condition, the sprue is designed with a taper, so that the volume flow rate, which is velocity into area VA, is same at the top and the bottom of the sprue. So so the fluid flow will be governed with the continuity, law of continuity, and which will be equals to V1A1 equals to V2A2. And with the tapered sprue, the fluid velocity is reduced and the aspiration effect is eliminated. So now you have an idea that why the sprue column is of the tapered shape. And then for better understanding, let's recall it again. So we have to determine the sprue geometry to avoid aspiration effect. So we take the section and large section of the pouring basin. So this is the pouring basin, and then to it the sprue is joined, and we consider 3 points just at the surface of the this molten metal liquid, and 2 is the point just at the surface of or the initial area of the sprue, and third point is at the bottom of the sprue. So one is the free surface, 2 is the sprue top, third is the sprue bottom. So this is initial height of the molten metal liquid inside the pouring basin, and it can be taken as HC. And then from point 3 to point 1, this height is taken as HT. And then you can simply apply the Bernoulli equation between point 1 and point 3, which is equals to P1 plus rho you can apply a Bernoulli equation between point 1 and point 3, and it will be P1 plus rho V1 square by 2 plus rho GH1, and this will be constant. So point 1 and point 3. So now you assume the entire mold is at the atmospheric pressure, and the metal in the pouring basin is at the zero velocity. So easily you can calculate the velocity of the this molten metal at point 3, which will come out to be root 2 GH. Here h is equals to the ht is the total height. And then similarly, you can apply the same equation between point 2 and point 3 in order to determine or to calculate the geometry of this pouring sprue. So P1 again will having the same formula, P1 plus rho V1 square by 2 plus rho GH1 equals to P2 plus rho V2 square by 2 plus rho GH2. And again you can calculate this V2 velocity between point 1 and point 2, and by equation of continuity, because this flow rate will be whatever be the flow rate, it will be same here and here. So by equation of continuity you can easily apply this A2 V2 equals to A3 V3, and from here A3 upon A2 equals to V2 upon V3 equals to under root HC by T. So from this correlation you can easily determine that what should be the diameter or the area of the sprue at this particular end, and what should be the diameter of your sprue at this end. So if you like the video, then please subscribe to my channel, share it with your friends, and don't forget to hit the bell icon for the latest updates. Thanks for watching my videos.